Good day, everyone. Today we're going to talk about Unit 1, the basics of surveying. Surveying is one of the oldest arts practiced by man. It has always been necessary to mark boundaries and divide land parcels tracts since the earliest times. Planning and design are based on the results of surveys, and construction is controlled by surveying. The basic characteristics of all surveying operations are the delineation of a portion of the Earth's surface or subsurface, or the establishment of the position or boundary of some object on it.
Here are the concepts of surveying. The first thing that we're going to talk about is the definition of surveying. So what is surveying? It is an art of determining the position of points on or near the Earth's surface by means of measurements in the three elements of space, namely distance, direction, and elevation. It is also an art of measuring horizontal and vertical distance between objects, of measuring angles between lines, of determining the direction of lines, and of estimating points by predetermined angular and linear measurements. Surveying is the branch of applied mathematics which teaches the art of determining the area of any portion of the Earth's surface, the length and directions of the boundary lines, the contour of the first surface, and of accurately delineating the whole on paper. What are the uses of surveying? The first one is staking out of simple structures. The builder must know the placements and levels of building lines displayed on the construction blueprints on the ground before beginning strength excavation for a structure's foundation. These placements and levels of building lines include the foundation trench's exact length, width, depth, and position. Next is the surveying of small parcels of land. A survey is carried out to locate, describe, monument, and map a portion of the land's boundaries and corners. It could also contain the portion's terrain, as well as the position of buildings and other improvements. Next is the extensive surveys and construction of subdivisions, dams, bridges, railroads, highways, wharves, canals, missile and rocket launching sites, drainage, irrigation systems, and etc. Any project of any scale is built along the lines and positions determined by surveying during implementation. The data gathered from surveying also helps in establishing the planning and design of the blueprints and provides data that can use to determine the best course of action. Laying out of industrial equipment. Surveying relies for its accuracy and efficiency on having the right instruments to establish the location points for site boundaries, foundations, columns, center lines of walls, and other necessary structural parts. Preparing forestry and geological maps. Forest surveying is done in order to locate and mark lines or boundaries upon the ground and to furnish data in preparation of geological maps. Positioning massive and complex machinery. Surveying allows the positioning of massive and complex machinery in safe areas to protect the machinery from damage and workers from injuries and accidents. The last two are construction of ships and airplanes and exploration of extraterrestrial bodies. There are different types of surveying. The first one is plane surveying. It is a type of surveying in which the mean surface of the Earth is considered as a plane or flat, and the spheroidal shape is neglected. Plane surveying is done if the area of the survey is less than 250 square kilometers. As we know, Earth is spherical in shape, but its diameter is big enough to consider plane in small dimensions. It is mostly conducted by state agencies as well as private agencies. Geodetic surveying. It is a type of surveying in which the curved shape of the Earth is taken into account. It is carried out if the area exceeds over 250 square kilometers. The objective of this survey is to determine the precise position on the surface of the Earth of a system of widely distant points. Geodetic surveys are usually of a national character. These are mostly undertaken by government agencies to serve as a basis for the production of accurate base and topographic maps. These are the differences of plane surveying and geodetic surveying. As you can see, the plane surveying is flat and the geodetic surveying is curved because the true shape of the Earth was taken into account. There are secondary types or classifications of surveys. The first is the cadastral surveys. They are usually closed surveys which are undertaken in urban and rural locations for the purpose of determining and defining property lines and boundaries, corners, and areas. The next one is city surveys. They are surveys of the areas in and near a city for the purpose of planning expansions or improvements, locating property lines, fixing reference monuments, determining the physical features and configuration of land, and preparing maps. Next is the construction surveys. It is a survey which are undertaken at the construction site to provide data regarding grades, reference lines, dimensions, ground configurations, and the location and elevation of structures which are concerned to engineers, architects, and builders. Forestry surveys are a type of surveying streams in connection with forest management and mensuration, and the production and conservation of forest lands. Next is the hydrographic surveys. It is referred to surveying streams, lakes, reservoirs, harbors, oceans, and other bodies of water. These surveys are made up to map shorelines, chart the shape of areas underlying water surfaces, and measure the flow of streams. Industrial surveys, also known as optical tooling. It is the use of surveying techniques in shipbuilding, construction, and assembly of aircraft, layout and installation of heavy and complex machinery. Mine surveys is to determine the position of all underground excavation and mine structures, to fix surface boundaries of mining claims, determine geological formation, to calculate excavated volumes, and establish lines and grades for other related mining work. It is just basically a survey from the underground. Photogrammetric surveys are a type of survey which makes use of photographs taken with specially designed cameras, either from airplanes or ground stations. Next is the route surveys. It is the determination of alignment, grades, earthwork quantities, location of natural and artificial objects in connection with the planning, design, and construction of highways, railroads, pipelines, canals, transmission lines, and other linear projects. In order to acquire a right-of-way, servitude, or easement from the property owner being crossed. Lastly is the topographic surveys. It determines the shape of the ground and the location and elevation of natural and artificial features shown include such natural objects as hills, mountains, rivers, lakes, and relief of the ground surface.
Survey instrumentation, or the instruments used in surveying. First is the automatic level. A level is an optical instrument used to establish or verify points in the same horizontal plane in a process known as leveling, and is used in conjunction with the leveling staff to establish the relative height levels of objects or marks. It is widely used in surveying and construction to measure height differences and to transfer, measure, and set heights of known objects or marks. Next is the engineer's transit. Transit levels are very similar to builder's levels when the telescope of a transit level is locked into place. It works almost exactly like a builder's level. There is one main difference between a transit level and a builder's level. A transit level, when not locked into place, can tilt only vertically and has a very limited range of mobility. This differs from the builder's level, which can move horizontally in a complete circle. Transit levels with their vertical movement mechanism are great tools for measuring vertical angles. Transit levels are also preferred over the other leveling tools for establishing straight lines and as well as turning angles. Theodolite. A theodolite is a precision instrument used for measuring angles both horizontally and vertically. It can rotate along its horizontal axis as well as its vertical axis. Theodolites have a lot in common with transits. Both theodolites and transits can be used for similar projects, but there are slight differences between the two instruments. Transits use vernier scale and external graduated metal circles for angular readings. Theodolites use enclosed graduated circles, and angular readings are taken using an internal magnifying optical system. Theodolites tend to have a more precise reading and provide greater accuracy in measuring angles than transits do. Total station. It is an electronic transit theodolite integrated with electronic distant measurement, or EDM, to measure both vertical and horizontal angles and the slope distance from the instrument to a particular point, and an onboard computer to collect data and perform triangulation calculations. Other instruments and tools used in surveying. First is a steel tape. It is used to measure linear distances. Next is a rangefinder. It is used to measure the distance from the instrument to a selected point or object. Next is a plumb bob. It is used to establish a vertical line. A plumb bob consists of a piece of metal called a bob pointing downwards, which is attached to a cord. When the plumb bob is hanging free and not moving, the cord is vertical. A leveling rod. It is used to determine the height differences between 2 points to measure the height or depth of a point with respect to the datum. Range poles. It is used to mark the positions of stations beside the stations to range straight lines. And lastly, marking pins. It is used when measuring a distance with a survey chain. Now let's talk about the care and handling of these surveying instruments. Number 1. The level should always be kept in a box when it is not in use. Number 2. It should remain in its carrying case when transported to a work site or when it has to be moved to another distance setup or over raft terrain. Number 3. The level does not have to be detached from the tripod when transferring to another nearby station, provided that it is securely fastened to the tripod and is carried properly. When in open spaces, the level may be carried on the shoulder in preferably a near vertical position. The spindle is clamped slightly so that the telescope does not rotate when carried. It must be in full view of the person carrying it to avoid hitting into trees and underbushes. While in densely forested areas, the level should be cradled between the arms and held close to one's left or right chest. The spindle should be unclamped to allow the telescope to turn freely and give way readily to any pressure or possible collisions with an object.
Good day everyone, I am Anja Gayulan and today I will be reporting about surveying field notes and the field survey party. Surveying field notes are the only reliable and permanent record of all pertinent information, measurements, calculations, sketches, and observations made by the surveyor in the field. The quality of a surveyor's fieldwork is affected directly in the manner he or she keeps in his or her field record. This means that if these notes are not clear and complete, the field survey was of little value. It is therefore necessary that the field notes contain a complete record of all the measurements made during the survey and that they include, where necessary, sketches and narrations to clarify the notes. In taking these notes, surveyors use the field notebook. The field notebook should be of good quality rag paper with stiff board or leather cover made to withstand hard usage and of pocket size. The different types of notes are the following. First, we have sketches. Sketches add much to clarify field notes and should be used liberally when applicable. They may be drawn to an approximate scale or important details may be exaggerated for clarity. Measurements should be directly added on the sketch or keyed in some way to the tabular data. An important requirement of a sketch is legibility, so the sketch must be drawn clearly and be large enough to be understandable. Next, we have the tabulations. The tabulations containing recorded measurements can also be supplemented with descriptions. The description may be only 1 or 2 words to clarify their measurements. The explanatory notes about a particular reading should be written on the same horizontal line as the reading, and if computations are necessary, they should be contained to the back pages of the field notebook. And lastly, the combination of the above mentioned. Next, we're going to be discussing about the field survey party. The field survey party is a crew of workers or professionals that work together to conduct a survey in the field. First, we have the chief of party. The chief of party is the person who is responsible for the overall direction, supervision, and operational control of the survey party. Secondly, we have the assistant chief of party. The assistant chief of party assists the chief of party in the accomplishment of the tasks assigned to the survey party. The instrument man. The instrument man is the person who sets up, level, and operate surveying instruments such as a transit, engineer's level, theodolite, plane table and alidade, and etc. The technician. The technician is responsible for use and operation of all electronic instruments required in a fieldwork operation. The computer. The computer performs all computations of survey data and works out necessary computational checks required in a fieldwork operation. Next, we have the recorder. The recorder keeps a record of all sketches, drawings, measurements, and observations taken or needed for a fieldwork operation. The head tape man. The head tape man is responsible for the accuracy and speed of all linear measurements with tape. And the rear tape man assists the head tape man during taping operations and in other related work. The flagman. The flagman is a person holding the flagpole or range pole at selected points as directed by the instrument man during operation. Next is the rodman. The rodman holds a stadia or levering rod when sights are to be taken on it. The pacer. The pacer checks all linear measurements made by the tape man. Next is the axeman or the lineman. The axeman or lineman clears the line of sight of trees, bush, and other obstructions in a wooded country. The aidman. The aidman render first aid treatment to members of the survey party who are involved in cases involving their health, safety, and well-being. Lastly, the utility man. The utility men render other forms of assistance needed by the survey party. All members of the field survey party work closely together to execute the survey work.
Now let us move on to our next topic, which is accuracy of measurements. A measurement is the process of determining the extent, size, or dimensions of a particular quantity in comparison to a given standard. In surveying, measurements are usually concentrated on angles, elevations, times, lines, areas, and volumes. In surveying, measurements may be made directly or indirectly. A direct measurement is a comparison of the measured quantity with a standard measuring unit or units employed for measuring a quantity of that kind. Some common examples are applying a wire or tape to a line, determining a horizontal or vertical angle with a transit, and fitting a protractor between two intersecting lines to determine the intersection angle. When it is not possible to apply a measuring instrument directly to a quantity to be measured, an indirect measurement is made. In this type of measurement, the observed value is determined by its relationship to some other known values. It is important for surveyors and students of surveying to have a good working knowledge of trigonometry and geometry. Here are some other examples of indirect measurements. The International System of Units, also known as SI, is based on the metric system. It began as the legal system of measurement in France during the 1800s. When using SI, all linear measurements are based upon the meter. Larger and smaller units are derived from it in decimal steps, and their names are formed by adding prefixes. Units in SI of major concern to surveying are meter for linear measure, square meter for areas, cubic meter for volume, and radian for angles. There are certain units which are not part of SI but are still widely used. These are kilometer for longer distances, hectare for larger areas, degrees, minutes, seconds for plane angles. Here are some of the commonly used SI prefixes which are added to basic names. These are mega, kilo, hecto, deca, deci, centi, milli, micro, and nano. The common units for length are kilometer, meter, centimeters, and millimeter. The unit of area in SI is the square meter. The following are the commonly used relationships. 1 hectare is equivalent to 10,000 square meters. 1 acre is equivalent to 100 square meters. 1 square kilometer is equivalent to 1 million square meters and is equivalent to 100 hectare. The common metric units for volume are the cubic meter, liter, and milliliter. The SI unit for plane angles is the radian. The radian is defined as an angle subtended by an arc of a circle having a length equal to the radius of the circle. 2 radian is equivalent to 360 degrees. In the Philippines, the sexagesimal units are used with SI because of their practical importance and our familiarity with it. Examples of sexagesimal units are degree, minute, and second, and an example of centesimal unit is grad. An error is the difference between the true value and the measured value of a quantity inherent in all measurements and result from sources which cannot be avoided. On the other hand, mistakes are caused by inaccuracies in measurements which occurred because some aspect of a surveying operation is performed by the surveyor with carelessness, inattention, poor judgment, and improper execution. Mistakes are also caused by misunderstanding of the problem, inexperience, and the indifference of the surveyor. Mistakes which are frequently committed include reading the wrong graduation of the tape, transposition of figures, reading a scale backward, misplacing a decimal point, and incorrect reading of field notes. Systematic errors are caused by the surveying equipment, observation methods, and certain environmental factors. Under the same measurement conditions, these errors will have the same magnitude and direction, which are positive or negative. Examples of systematic errors are using incorrect temperature and or pressure observations, not applying curvature and refraction constants, using incorrect instrument heights and or target heights, using an incorrect prism offset, and using an imperfectly adjusted instrument. Can minimize these systematic errors by properly leveling the survey instrument on targets, balancing foresight and backsight observations, entering the correct instrument heights, target heights, and prism offset in the data collector, and periodically calibrating the surveying equipment. Accidental errors are errors that are purely accidental in character. These are caused by factors beyond the control of the surveyor and are present in all surveying measurements. The occurrence of such errors are matters of chance as they are likely to be positive or negative, and may tend in part to compensate or average out according to laws of probability. Instrumental errors are due to imperfections in the instrument used, either from faults in their construction or improper adjustments between the different parts prior to their use. Natural errors are caused by variations in the phenomena of nature such as temperature, wind, curvature of the earth, gravity, humidity, and refraction changes in magnetic declination. Personal errors arise from limitations of the senses of sight, touch, and hearing of the human observer which are likely to be erroneous or inaccurate. Typical of these errors include error in determining a reading on a rod which is out of plumb during sighting, error in the measurement of a vertical angle when the crosshairs of the telescope are not positioned correctly on the target, and making an erroneous estimate of the required pole to be applied on a steel tape during measurement.
Accuracy indicates how close a given measurement is to the absolute or true value of the quantity measured. Precision, on the other hand, refers to the degree of refinement and consistency with which any physical measurement is made. It is portrayed by the closeness to one another of a set of repeated measurements of a quantity. When gathering data, high accuracy is much preferred along with precision to obtain best results. Factors affecting accuracy and precision of one's collected data may be the quality of one's instruments or one's methodology. Probability is the the number of times something will probably occur over the range of possible occurrences. It is a number that reflects the chance or likelihood that a particular event will occur over the range of possible occurrences. It can be expressed as proportions that range from 0 to 1 or 0% to 100%. The theory of probability is based upon the following assumptions relative to the occurrences of errors, such as small errors which occur more often than large ones and that they are more probable. Large errors, which happen infrequently and are therefore less probable. For normally distributed errors, unusually large ones may be mistakes rather than accidental errors. Positive and negative errors of the same size happen with equal frequency, that is, they are equally probable. And lastly, the mean of an infinite number of observations is the most probable value. The most probable value is an arithmetic mean or average of related measurements that have the same precision. It refers to the quantity which, based on available data, has more chances of being correct than any other. If a given quantity is measured more than one time, not all the derived values are correct. There is only one correct value that should be considered, and it is determined by the formula of MPV, which is the summation of measurements over the number of measurements. In the sample problem for MPV, we are provided with 6 different values, so we have a total number of 6 measurements. So using the formula for MPV, we input the summation of the 6 values over the number of measurements, which is 6, and we get the total of 250.51 meters. In the second example, we see that the problem involves condition. So based on the illustration, the 3 values form one complete rotation or a circle. So we all know that one circle or one cycle should sum up to 360 degrees. So to determine the most probable value of each angle, we start with determining the correction to be applied. So we use the formula sum equals angle 1 plus angle 2 plus angle 3, and it sums up to 360 degrees and 30 seconds. So there is a discrepancy of 30 seconds. So for the correction, we use the formula discrepancy over n. So 30 seconds over 3, which gives us 10 seconds. After getting the correction, we then determine the most probable values. So using the formula as seen on the screen, we get the probable values for each angle. And when we sum up the MPV for each angle from the first to the third angle, it sums up to 360 degrees, which is correct. Relative precision describes the precision of distance measurement in surveying. The total amount of error in a given measurement should relate to the magnitude of the measured quantity in order to indicate the accuracy of a measurement. It is expressed by a fraction having the magnitude of the error in the numerator and the magnitude of a measured quantity in the denominator. So the formula for relative precision is given by RP equals probable error of the mean over the most probable value of the measurement, which is denoted by RP equals PE over MPV. Probable error is the amount by which the arithmetic mean of a sample is expected to deviate from the true population mean because of chance alone. A quantity which, when added to and subtracted from the most probable value, defines a range within which there is a 50% chance that the true value of the measured quantity lies inside or outside the limits thus set. In the sample problem for probable error, we are given the following measurements of a line. We are then asked to determine the MPV of the measured length, the probable error of a single measurement and probable error of the mean, the final expression for the most probable length, and the relative precision of the measurement. So for the MPV, we add up all the given measurements and divide it by the number of measurements, which is 6, and it then gives us 1000.45. Next, we are asked to determine the probable error of a single measurement and probable error of the mean. So for the probable error of a single measurement, we are given the formula plus minus 0.6745 multiplied by the square root of the summation of the squares of the residuals over the number of observations. We then substitute and plug in the respective givens. Then we get the probable error of plus minus 0.05029 or plus minus 0.05. For the probable error of the mean, we are given with the formula plus minus 0.6745 multiplied by the square root of the summation of the squares of the residuals over the number of observations multiplied by the number of observations minus 1. It will then give us plus minus 0.02053 or plus minus 0.02. After plugging in the respective givens and substituting them into the formula. For the final expression for the most probable length, we are given the formula MPV plus minus probable error of the mean, so we plug in 1000.45 plus minus 0.02. Therefore, the most probable length is between 1000.43 meters and 1000.47 meters. Lastly, we are asked to determine the relative precision of the measurement, so we use the formula RP equals probable error of the mean over the most probable value of the measurement. So, we substitute the respective givens and then we get the respective answers for each relative precision of the measurement. So for the relative precision of the single measurement, we got 1 over 20,000 and the relative precision of the mean is equal to 1 over 50,000. In weighted observation, the weight of an observation is a measure of an observation's relative worth compared to other observations. Weight is directly proportional to the number of observations. We are then given the formula W equals Kn. On the other hand, weight is inversely proportional to the square of the error. We are given the formula W equals K over E squared. A weighted observation, also known as the most probable value, is the mean value computed from weighted observations only for one quantity with different weight. The formula for weighted mean is equal to the summation of weighted observation over the summation of weight. In the sample problem for weighted observations, we are given with 4 measurements of a distance and we are asked to determine the weighted mean. Following the formula, we add up all the weighted observations and we get 2,842.02 and divide it by the summation of weight, which we add up and totals to 10. Then we get the weighted mean of 284.202.
Next, I am going to discuss survey methods for accurate distance measuring. What is the measurement of distance in surveying? It is the accurate determination of distance between 2 points on any surface, which is one of the basic operations of plane surveying. Linear measurements of distance are understood to mean the horizontal distance. There are several methods of determining distance, and we'll be discussing them shortly. First is pacing. Pacing consists of counting the number of steps or paces in a required distance. A pace is defined as the length of step in walking. To pace a distance, it is necessary to first determine the length of one's pace, which is referred to as the pace factor, and to walk naturally and carefully in a straight line when calibrating one's pace and in pacing distances. Next is tachymetry. Tachymetry is another procedure of obtaining horizontal distances. It is based on the optical geometry of the instruments employed and is an indirect method of measurement. Tachymetric measurements are performed either by the stadium method or the subtense bar method. The stadium method is a rapid means of determining horizontal distances in which distances and elevations are obtained by observing the interval on a graduated upright rod called the stadia rod, intercepted by 2 parallel horizontal lines equipped in the telescope called the stadia hairs or wires, in a surveyor's transit set up at a distance from the rod. The subtense bar method is a convenient and practical device used for quick and accurate measurement of horizontal distances. The procedure for determining the distances between the points is done by setting up the subtense bar at a distant station, and then measuring the horizontal angle subtended by the distance between the 2 targets. Next, we have the graphical and mathematical methods, wherein unknown distances may be determined through their relationship with known distances geometrically through employing plane table surveys and triangulation works. Distance can also be measured through mechanical devices. These devices are only applicable for low precision surveys or where quick measurements are desired. The more commonly used among these devices include the measuring wheel, odometer, and the optical rangefinder. The measuring wheel, also known as surveyor's wheel, is a tool used to measure distances. An odometer is a device attached to the surveyor's wheel, which counts the number of rotations and uses the circumference of the wheel to calculate the distance covered. The optical rangefinder is a device which is used to determine distances approximately simply by focusing through the eyepiece and sighting a distant object, which defines the other end of a line to be measured.
The next survey method is photogrammetry. Photogrammetry refers to measurement of images on a photograph. It can be defined as the science of making reliable measurements using photographs or digital photo imagery to locate features on or above the surface of the Earth. Photogrammetry is traditionally used to create topographic maps from aerial and spatial imagery. The next survey method is by the use of electronic distance measurement. Electronic distance measurement, or EDM, is a method of determining the length between 2 points using electromagnetic waves. EDM is commonly carried out with digital instruments called theodolites. EDM instruments are highly reliable and convenient pieces of surveying equipment and can be used to measure distances of up to 100 kilometers. The last survey method is taping. Taping is the linear measurement of the horizontal distance between 2 points using a surveyor's tape. Tapes are issued in various lengths and widths and graduated in variety of ways. The following are conditions which could exist during a taping operation. These conditions are common mistakes and errors that may occur when taping. First is the substandard or nominal lengths due to either faults in their manufacture or damages to the tape. The next condition is the ends of the tape are not held at the same level when breaking tape along inclined or rough terrain surfaces. Next is the inaccuracy in keeping the tape along a straight line. Next is the tape is not of nominal length due to the difference in the temperature prevailing during the actual measurement. Next is the shortening or lengthening of the tape due to the application of pull applied on the tape. And the last condition is the distance between the endpoints of an unsupported length of tape is less than the specified nominal length. Next, we will talk about the different procedures of taping. The first step when taping is aligning the tape. It is important to make sure that both ends of the line that are to be measured are marked. This is to establish guide points in order to make it easier to obtain a straight line. The next step is stretching the tape. A steady and firm pull is applied on one end of the tape during stretching. There should be no measuring done prior to stretching, as tapes are correct in length only when a standard pull is applied to the tape. After stretching the tape, the next step is plumbing. Each end of the tape is marked by positioning at plumb line. Both ends of the tape should be held above ground, about the level of the waist or chest, and in a horizontal position. Next is marking full tape lengths. The rear tape man holds his end of the tape opposite to the pin earlier set on the ground. The head tape man will then exert the required pull on the tape after being lined in properly. The next step is tallying tape measurements. At the initial point, the rear tape man holds one pin and the head tape man begin with 10 pins carried on his steel rings. And the last step is measuring fractional lengths. When the last segment of line is to be measured, this will often be a measurement which will consist of a fractional tape length. Next, we will talk about tape correction. In surveying, tape correction refers to correcting measurements for the effect of slope angle, expansion or contraction due to temperature, and the tape sag, which varies with the applied tension. The purpose of this is to add a correction if the tape is too short or subtract if the tape is too long. The first type of tape correction is tape correction due to pull. During calibration, or otherwise known as standardization, a tape is subjected to a certain amount of standard pull or tension on its end. The tape stretches in an elastic manner, and since the modulus of elasticity of a material can be expressed as the ratio of unit stress to unit elongation, the change in length can be determined as follows. E is equal to the unit stress over elongation per unit length. These are the formulas associated with tape correction due to pull. Cp is equal to Pm minus Ps multiplied by L over Ae, where Cp is the total elongation in tape length due to pull or the correction due to incorrect pull applied on tape in meters. Pm is the pull applied to the tape during measurement in kilograms. Ps is the standard pull for the tape or pull for which the tape is calibrated in kilograms. L is the measured length of the line in meters. A is the cross-sectional area of the tape in square centimeters. E is the modulus of elasticity of the tape in kilogram per square meter. And L apostrophe is the corrected length of the measured line in meters. Next is tape correction due to temperature. The tape lengthens as the temperature rises and shortens as the temperature falls. The correction applied to the length of the tape due to change in temperature Ct is given by the formula Ct is equal to Cl multiplied by T minus Ts, where C is the coefficient of linear expansion, L is the length of tape or length of the line measured, T is the observed temperature of the tape at the time of measurement, and Ts is the temperature at which the tape standardizes. Next is tape correction due to sag. The correction due to sag is the difference in length between the arc formed by the tape and the subtending cord. The formula is Cs equals W squared multiplied by L over 24p squared, where W is the total weight of the tape between supports in kilograms, and P is the tension or pull applied on the tape. And lastly is tape correction due to slope. The equivalent horizontal distance may correspondingly be determined by applying approximate slope correction. And the formula is CH equals h squared over s plus d, where h is the height of the slope, d is the horizontal distance, and s is the slope distance between 2 points on the slope line. The correction for the effects of incorrect length of tape, temperature, tension, slope, and sag may be combined as a single net correction per tape length. Since the sign of each correction can be determined during computation, it is then a matter of adding these quantities algebraically to arrive at a single and overall correction to lengths. Here we have a sample problem for tape correction due to temperature. A steel tape, known to be of standard length at 20 degrees Celsius, is used in laying out a runway of 2,500 meters long. If its coefficient of linear expansion is 0.0000116 per 1 degree Celsius, determine the temperature correction and the correct length to be laid out when the temperature is 42 degrees Celsius. In order to solve this, we first have to write the given in the problem. Given, the temperature at which the tape standardized is equal to 20 degrees Celsius. The length of the line is 2,500 meters. The coefficient of linear expansion is 0.000116 per 1 degree Celsius, and the observed temperature of the tape at the time of measurement is 42 degrees Celsius. We will then use the formula Ct is equal to Cl multiplied by T minus Ts. Substitute the given values into the formula to solve for Ct. After solving, the value that we get is positive 0.638 meters. The positive sign here indicates that the tape is too long. Hence, we should subtract 0.638 meters to 2,500 meters. Therefore, the final answer would be 2,499.36 meters, which is the correct length to be laid out. Thank you for listening. That is all for Unit 1, the basics of surveying. We hope you learned a lot from our discussion, and you may check the module found in Canvas for more reference about Unit 1.